So we've talked about enthalpy so far, but one of the most important things is to consider what the reaction enthalpy is for any individual reaction. And you know how we've been looking at molecular equations in the previous chapter. Molecular equations, ionic equations. I'm about to introduce another type of equation that's called the thermochemical equation. So this right here is a thermochemical equation. Notice what it looks like. It looks exactly like a molecular equation, except it's got this delta H reaction over here on the side. So what this is saying is this is actually showing the energy or the heat that's either absorbed or released from the reaction. It's showing it as kind of one of the products or reactants. If the delta H of reaction is negative, remember that means that the reaction is releasing heat to the surroundings, and so heat is a product. If it's a positive value, it means it's absorbing heat from the surroundings, and that would indicate that the heat is kind of like a reactant. And so when you're thinking about this, consider the heat as either a product or a reactant of the reaction. Now also, very important is remember how we use stoichiometry. We use these coefficients on here to show what the relationship on a mole to mole or atom to atom or molecule to molecule basis is. Well, this heat is also given on a molar basis. So for every 2 moles of hydrogen in this reaction, if you react it with enough to completely react 2 moles of hydrogen, you get this much heat. This much heat. If you have 1 mole of oxygen and you react it with enough hydrogen to completely react it, you get this much heat. But if you only had half a mole of oxygen and did this reaction, then ran it to completion, you'd only get half as much heat released. So if you ended up doubling all of these values, you would end up getting double the amount of heat, and so on and so forth. So we were able to do stoichiometry with these thermochemical equations and figure out how much heat we're going to be producing uh, based on the equation and how much reactant we have. So this delta H reaction, this is the enthalpy for the reaction, or the heat of the reaction. So if I use that term, just recall that I'm just talking about how much heat is giving off during the course of the reaction. And it is dependent on the number of moles. That's what I was saying about the stoichiometry. You need this many moles of this many moles of that to get this much heat. If you only have half the moles up here, half the moles of the reactants, you only get half the heat. If you have double the moles of reactants, you get double the heat. So anyway, so the delta H of a reaction means that this much heat is released to the surroundings when 2 moles of water are formed. See how many moles of water are formed? If we end up forming more moles of water, that means we reacted more of these reactants, we ended up using more heat. And notice that this is a balanced chemical equation. So just like on the molecular equations, these have to be balanced using the coefficients, not the subscripts, right? The subscripts are for balancing the compounds themselves. All right, so now that we've looked at this equation, or what this equation means, let's consider what it actually indicates on a large scale. Okay, so now we've seen the equation. So if you look at this, what we're doing is we're taking hydrogen, we're going through a redox reaction, and we're making water. And so what's going on here is if you did this on a large scale, actually not too large of a scale, you could actually fill up a balloon with hydrogen, give it a little bit of energy to get the reaction going, and you'd see that it would poof into a big pillar of flame. It's fantastic, actually. Very loud, very explosive, happens very fast. The reason why you see this big puff of flame is because of all the energy that's released so quickly. It's 483.6 kilojoules per 2 moles of this and 1 mole of that. So what we see is that the internal energy of the reactants here is significantly less than the internal energy of the products. And all that energy that is released during the reaction in order to get down to this lower energy is released as heat given off as heat during the course of the reaction. So a couple of things we need to point out about this enthalpy, or enthalpy of the reaction, the heat of the reaction, is that it is extensive. Okay, it does matter how much of your reactants you have. The more reactants you have, the more heat is given off. So if you consider the reaction below where you're burning methane, you take methane and one molecule, or 1 mole of methane, 2 moles of oxygen, goes to form one mole of carbon dioxide, 2 moles of water. It gives off this much energy when that occurs. So if we were to ask how much heat is released when 4.50 grams of methane gas is burned in a constant pressure system, this is assuming we have all of the oxygen we need to completely burn the methane. What we do is we have to use the methane, the mass of the methane, and convert it into moles of methane. Just like we did in chapter 3 and chapter 4, we're converting back into moles of methane so that we can do this direct conversion. So we take the methane, we use the molar mass of methane to convert it into moles. Notice the grams will cancel here, the grams will cancel here, and will be in units of moles of methane. And then the next thing we're using is we're saying that for every 1 mole of methane, we're getting 890 kilojoules. Where did we get this conversion from? If you look back at the balanced chemical equation, we see that there's a coefficient of 1 understood to be here, and 1 mole of methane will produce this much heat as long as we have enough of our oxygen to completely burn there. And so if we do this conversion, start with the mass of methane, convert it into the moles of methane, and then take away the moles of methane and convert that into how much heat is released, we end up with 250 kilojoules of heat released when you burn 4.5 grams of methane. Another important factor to understand here is that it depends on which direction you're going. So we said that we get 890 kilojoules if we burn 1 mole of methane. But if we were to do the opposite reaction and take carbon dioxide and water and form methane and oxygen, we would be able to do that, but we'd have to actually add energy back to the system. The same amount of energy that was released in the opposite reaction, we'd have to add that back in the form of heat. And so we would have to heat this reaction to get it to go. Remember that the reason why we can do this reverse reaction is because of the enthalpy is a state function. It doesn't matter how you get to where you're going. It's all dependent upon what state each of the products or reactants are in. And so we're able to do this reverse reaction because delta H, or the enthalpy, is a state function.